it on the chat and we can get going. Over to you, Shalaja.
Okay. Hi, hope everyone is doing good. Let me present. Yeah. Okay. So today we are going to design a object storage, something similar to S3 kind of object storage. And this is going to be interactive session. And forgive me, I have a bit of pain in my left eye. I think it's acute dryness. So I would like to split this session into one for 1 hour today and another 1 hour next week. So first, I will start with explaining the requirement. After that, we can together go into the designing the system. Designing object storage. Object storage is anything, something like storing lots of small amounts of data. For example, if you take our Google Photos, there are so many photos. Each of them are smaller in size, maybe like something like 4 MB, 2 MB, or something around. But but the quantity wise, those are huge. There are billions of users, and each user is storing many number of photos. But each photo could be in the size is could be smaller. So for this kind of system, it need not be just a Google Photos. It could be some other system like where you are storing many small files. For example, if you take your messaging system or WhatsApp or something, whenever the users exchange media, that media probably getting stored in object storage. Not about the videos. We'll come back to the videos. Videos are huge, bigger in the size, so they will probably go into the block storage depending on the requirement. But most of the times, the smaller images, emojis, those kind of things, which are smaller in the size but more in the quantity, those get into the object storage. So here we are developing a platform. So there's some object storage which can be used by any of these kind of applications. The object storage we develop, it could be used by the Google Photos or Apple Photos, or it could be by the messaging systems or any other system which needs to store lots of small size data. That's the reason. The important thing here is we are developing a platform, not a particular application. Applications use our platform and run on top of that. Similarly, the questions can vary in the interview. The interview can probably say that design object storage, or they probably say that S3 like storage system, or they can say that design a Google Apple Photos. So any kind of requirement which makes it to store many in the quantity was higher but size was smaller. That's when this kind of criteria, this kind of design works. So the solution is pretty much similar, maybe slight variations depending on the usage criteria, but overall the design is going to be very similar. Now, before jumping into the, usually in the interview, probably the interviewer will give you only this title, and from there you probably need to dig more, ask more questions into the interviewer, what exactly he is looking or she is looking for in the interview. But here, because we have beginners, I first need to explain what is a block storage, what is the file storage, what is the object storage, how do they differ, why we can't have just one system which works for everything. Once I explain this, once I give the fundamentals, then you can also contribute into the designing in the further steps. So usually what happens, let's assume you have a disk. Um, In the disk, every disk, usually a typical hard disk, comes with a 4 KB of the size of the blocks. So when hard disk is manufactured, that's when most of the times the block size is fixed, because reading in this amount, writing in this amount is efficient from the hard disk. So it's like a chunks of the 4K, 4K, 4K. So There may be some kind of storage systems where the block size can be tunable, but I suspect how are they. But most of the times, even including the flash storage, the block size is pretty much defined during the manufacturing when the controller is developed. It's not just the hardware. The every hard disk do have a controller as well. So that controller will is developed such a way that reading in the block size is efficient. So, for example, from 0 to 4K, one block, 4K to 8K, another block, so on. Now, if when you just assume that you just bought a hard disk, you got this kind of hard disk. On top of that, can you just write directly into the hard disk? Usually, no. So what you usually do, you format the hard disk, right? Whenever you buy external hard disk, you usually, whenever you attach to the laptop, it immediately says that do you want me to format. On the Windows, it's probably formatting in one format, and the Linux is probably formatting into another format. Depending on the file system, it formats accordingly. So what happening when you run say calling that format on the hard disk, what it is happening, it is writing a file system on top of that. So the file system, what does it do? It has the capability to read and write in the block sizes and do this in efficient manner. So when it is writing a file, for example, if it is writing a file expanding in these data blocks, then the file system do maintain a metadata layer visually for every file, one file, file one. Then there is a inode one. Inode is a internal structure within the file system that represents a file. So inode says that, okay, what kind of inode is it? Is it some special file? It could be normal regular file or binary file, so and so. And then how much size is it? And what are the actual data blocks are there? So actual data blocks need not be sitting always contiguous. So for example, this block 1, 2, 3, so on, and this is another block 6, let's say. The data 2 and could be written 2 and 3 data blocks, and the next data when it is getting written, when the file is getting appended, the data probably go into the 6. So the inode, this is the file system structure which is maintaining the mapping of data blocks to the corresponding file. So, and it's in fact much more complicated than what I simply mentioned here. I can suggest you the reference material to really understand the internals of the file system, but this is how the file storage is. Now, file systems are, the file format storage systems are optimized for anything like file level operations, opening a file, creating a new file, appending the data, and then deleting the data, in place updates to the file, and then closing it, so on. The file systems also take advantage of the block size of the hard disk for the best performance. The file system itself can do its own caching, it can do its own write-ahead logging, and so on. So now coming to the block storage, when do we use block storage? When we want to bypass the file system altogether and we want to have our own custom layer. For example, if you take a Docker, or I'm not sure is Docker doing that, but for example, if you take a virtual machine, the virtual machine, when you're creating running a virtual machine on your system, you usually give a hard drive to this one. For example, in the Windows, it could be D drive or something. On the ext on the Linux, it could be some ext3 formatted. Sorry, this is the block storage, right? So some mounted. Let's say I mounted something like volume 1, and then I gave it to the virtual machine. So what does virtual machine do? Instead of using the file system, it does its own file storage layer. So probably it similarly maintains the metadata layer, but in its own required format. If you remember, if you attended the last design for the Kafka, we used the sequential log structure storage. For that one, we used our own custom storage. We didn't use a database or NoSQL. I did explain why we wanted to go with that. In those kind of systems, in a real Kafka kind of higher-end systems, they probably want to just bypass the file system because instead of that, they wanted to develop their own storage layer, which is more efficient. So in this case, the block file system, we can say block storage. So the block storage is handed over to the higher level application. The higher level application will use it will rewrite the metadata. It will use the blocks accordingly as per its requirement. Now, coming to the object storage. When we use object storage, in case of object storage, the data, the files we are writing could be quite smaller. So, for example, if I'm writing to the, let's say, because S3 is popular, I'm writing to the S3 one file and file F1, another file F2. Or you can just take a Google Photos. It's more easy to map to the application. Let's say I'm writing photo 1 and photo 2. Photo 1 probably occupying only partial data block. Photo 2 probably occupying another partial data block. That means the actual entire size of a block is not efficiently used. Only partially it is used. Even though we are writing only part of the block, for the disk, any operation, any read-write operation has to happen on the entire 4K. So in that case, what object storage does, it brings the data block into the memory, writes it, and it keeps it there until it is filled. It keeps writing more and more objects, and it keeps it there, and it's in flush. It does the flush. So when object storage does this, it has to take into the consideration how it is ensuring the durability when there is a system crash, how is it is ensuring the consistency. So all those scenarios the object storage has to take care of. Not only that, the metadata layer for the object storage also going to change, because there are many more objects, and which are a smaller size. The metadata size also going to be quite huge, because for each object 1 where it is written, object 2 where it is written. So you are going to have many uh, if there are billions or trillions of the objects, you are going to have trillions of the records, and each of them going to be very small in the size. So this kind of storage format is suitable for the object storage. So object storage, the storage layer is developed to be efficient for that kind of access pattern. So what you need to remember, block storage. When do you need to use the block storage? When some application is doing its own storage layer efficiently at the block level. So it could be a virtual machine. Usually these are bigger things which really need to maintain lots of amounts of the data, and each data write operation is huge. In those cases, they do bypass the file system, directly work at the block layer. So those are usually bigger applications, and the size of the data is bigger. Then file system. File system you already know. We use for typical regular files, creation, append, etc. So on. So. And then object storage. When do we use object storage? This is access pattern we need to be good in understanding, because based on the access pattern, we choose the appropriate design. When there are smaller sized files or the data, but there are the amount of data is huge, quantity is huge, that's when we go for the object storage. So now here, if you see, in case of Google Photos or in case of S3, almost everyone in the world is using S3, but the size of the data, each and every object we are writing into the S3 varies drastically. Maybe I am writing a small files. The companies who are buying storage from the AWS, they are probably writing bigger size files, or someone developing an application, something like photos on top of the S3, probably they are writing medium to small size. So the size of the objects vary drastically, but the amount of the quantity of the data is going to be quite huge. So these kind of access patterns are suitable for the object storage. Is that clear? Because from here, if you don't understand why we really need object storage, it becomes difficult for you to design a system for this one. If you have any questions on this one, do ask me now. So everyone is clear about this, right? How small is considered as a small file? So small, we can't relatively say that, but usually access pattern, if you observe, when you're reading and writing to the disk, usually the block size is 4K. So any read and write operations usually 4K or in multiples of 4K. are efficient with the file and block storage. But if the size of the file can be smaller than 4K or need not be multiple of 4K, even if it is, for example, 5K. If you're writing 5K, 4K, we are writing in one block, but still 1K is leftovers. And this can happen in block storage and file storage as well. There can always be fragmentation. For example, I'll show you. Let's assume this is a disk block and this is another disk block. This is 4K, this is 4K. When you're writing 5K, what happens? 4K gets filled out here. The 5 in another 1K gets filled out here. This is going to be empty. When such so many fragments gets left over, what does the file system do? It tries to do the compaction. It tries to move the data together in every periodically every few seconds to reduce the wastage of the space. See, this space is got wasted, so it reduces. But this compaction is really very disk intensive because it has to read the data from another place, read it from here, write it here, and then that means you are moving the data, reading from one place and writing to another place. This requires read and write operations. That is the one thing. And second thing, some kind of file systems, block storages, they don't write two different files data into the same block. In fact, actually, almost every file system they don't, because for every one block, there is a header and the trailer, etc. So they don't reuse the same block for two different files. It can be for the same file, but not two different files. So there is always a fragmentation possible in any kind of storage. But in object storage, it is much more possible because there are the size of the objects is not aligned with the 4K. Most of the time it's smaller than the 4K. Most of the time it is smaller than the 4K. Then it is definitely suitable for the object storage. And even if it is sometimes more than the 4K, but not going to be quite frequent or can going to create a lot of fragmentations, then it's also suitable for object storage. So yes, S3 do support objects of size bigger than 4K, but usually if you see the access pattern, most of the times it's not like a very big files. This is many small files, but huge number of files. So the object storage we develop, we don't really say that the only this much size it is, then only we are going to use object storage. We do support bigger files as well. We come with the design which is going to support bigger files as well. But what we need to keep in mind that our system is mainly tailored for this kind of access pattern where size is smaller, but there are a huge number of files. That's the access pattern for the object storage. So if you take a Google Photos or if you take a music media, so most of the times those files are smaller, but there are huge number of files. Did I answer your question? So are there any more questions before going with the design? Now I'm going to ask you questions. That's why better you ask me now. Okay. Now you understand why we need object storage, what kind of access pattern it is, what kind of applications usually use this object storage. Now, assuming that you and me together starting a startup, we want to develop object storage. We are the founders. We are going to platform as a service, the object storage platform as a service here. So our customers can be someone XYZ Photos. Our customers can be XYZ Media, streaming music media company, or it could be some kind of similar to WhatsApp, my app, something which is messaging. So our object storage that we are going to design, it should be able to tailor most of these requirements. Now tell me, what are the functional requirements in this case? So what are the functional requirements for our, see, you're all the founders now. No, you need to answer.
So maybe to be able to store small data like efficiently.
Yeah. Next. Fast read, yes. Fast storage, we can say that latency, yes, in any kind of storage, always latency plays a big role. But compared to, there is one difference. Oops, where am I? Oh, I am using Excalibur in two different places, so it's bothering me now. Yeah. Uh, Small files. Uh, I need to upgrade my iPad. This one is quite old. That doesn't write well with the pencil. And then, yes, fast read, usually we call it as a low latency. And this is usually non-functional requirement. But yes, for any kind of storage system, because storage systems are usually used for reading and writing data, which is really needed by the critical application to make decisions. For example, if you are developing a driving navigation system, so you are driving a car and you're trying to read some data from the S3 on the time to see the route navigation. At that time, we should be able to read that data immediately from the S3 as soon as possible. So low latency is important, but always, because the moment when you say S3 kind of system, this one is sitting somewhere on the web. The data center could be in different country or different location as well. So compared to the our own data center, the S3 kind of latency is going to be higher because the network is involved in the web, whereas in case of data center is our internal network only, which can be, we can use faster networking within the company as well. So compared to that, usually for S3 kind of system, which is sitting somewhere in the web, is going to have a slightly higher latency. Yeah, but it's low latency is still a requirement because we are not saying that we are going to do only S3 kind of system. Our object storage could be in our own data center and we're selling the service. Yes. Next one, accessibility. Yes, so we develop APIs for accessibility. So in the accessibility, what are the operations are you going to have? So what are the operations you usually do on the object storage? Assume that you are the customer, you're using object storage. What operations do you do?
Read and
Yes,
write.
yes, read and
Re-
write.
Read object. So obviously we have to write an object. Yes, write an object, read an object, then
Save. Like, yeah,
yeah,
but
write
write
is
is
the
same.
same.
Yeah, same. Yeah.
So we can call it as a durability. The moment we have write it, it has to be persisted no matter whatever is our design. Durability means when I said to the customer that okay, I have taken your write, and it doesn't matter are you writing it a disk immediately or later, doesn't matter, you have to ensure that that data is definitely going to exist in your system or you're going to recover it. So that's, we call it durability. And the other one, so usually in S3, there are buckets. Similarly, in Google Photos, you have albums. So what we can do is buckets are something like just a logical entity to categorize set of files or set of photos into one unit. So we can say that create create a bucket, or you can say album in case of the Google Photos. So create a bucket, that is one operation. And whenever you're doing read and write, you should have the option to delete as well, of course. Delete object. And what else? Yes, delete, there is, you answered that. Do you need backup in case of data correction? Obviously, every storage system do have a backup. That's also a kind of non-functional because we don't have to mention, but we always have to maintain a backup in the background, even though customer did ask or doesn't ask, we have to maintain. So that's a backup, but usually in the system design interviews, we keep it as optional unless interviews are asked, because it will take time to explain a backup strategy. Once we design a system, that's when we can have a background process to do the backup strategy. So we usually keep it as optional and good to have for the later. And then put get, yes, so we'll come to the APIs for the corresponding read and write operations. Metadata storage, yes, we do internally maintain metadata. Consistency and durability, yes, this comes under non-functional requirements. So customer asking or not doesn't matter, we have to maintain them from our side. So coming to consistency, there are trade-offs. Do you want to go for eventual consistency or strong consistency? So, when we are providing any storage system, the platform as a service, we are providing platform as service. Our you customers can be very different. Some customers may need eventual consistency. Some customers may need strong consistency. In that case, what we want to do is we should always provide an option to give strong consistency. So some systems, what they do, for example, yesterday, they always give strong consistency. Some systems can give an option to configure. If you want, if the application doesn't want to have the performance penalty of a strong consistency, they can give an option. But I always recommend in the interview, whenever you're providing any storage system, near object, any storage system as a service, always go for strong consistency, because storage we cannot compromise on the consistency. We cannot give older data when it is as a service. When you are developing your own application based on your application requirements, you can change it. But here you are developing a platform, not an application. So always go for the strong consistency. So in our case, we assume it's a strong consistency. And then durability, yes, we did write it. And API support will come for APIs here. Then to retrieve files efficiently is exactly correct. Yeah. So creating buckets, read, write, delete objects, small files, and then again, they are good to have encryption, because whenever we are dealing with the data of the someone else's data and we are storing someone else's data, always we need to have encryption. But in the interviewer, we can say that it's I will explore it later if I have time. So it's a good to have. You can mention that we need to have encryption, but because of the time consideration, I will look into the encryption later on if I have time. Okay, that you can say encryption and access control, like authentication, authorization. Again, any system, whatever we develop, it has to have the access control, and you can always keep it as a good to have, and you can speak about it only if you have time. Okay. Yeah. Now coming to non-functional requirement, we covered most of them. Yes, encryption and access control, and then low latency, durability, backup, consistency, availability. So because we are providing a storage platform as a service, we always need to have a SLAs, because the moment our customers, they don't see we are meeting with SLAs, they walk away from us. So we need to ensure that it is high availability. But if we see the trade-off, whenever we provide strong consistency, if we remember our CAP theorem, we can either have always available system with eventual consistency, or high availability system with strong consistency, but at times we may not have the system available, because if we need strong consistency, there can be scenarios where we probably not we probably not replicated the data to the other side yet, and system part of the system has gone down. So in those cases, we always go for the, if we are going for the strong consistency, we go for the high availability, something like 99.999 and something. I think yesterday was 11 nines, I guess. So, but we don't say 100%, because it's not eventual consistency. In case you forget the CAP theorem, do let me know. I will try to recollect it for you. Otherwise, you can go back to the video and look into the recording again, why we wanted to compromise always between strong consistency with the 100% availability or high availability versus eventual consistency here, the CAP theorem. Now coming to the APIs that you discussed, so we can just write. See here, we are assuming S3 kind of system. That is something web APIs. So we can use REST APIs. REST APIs, if you are not aware of them, it's not a big thing. Just some guidelines. There is nothing wrong in writing our own stupid REST API, not really following the RESTful pattern. For example, I can say get the guidelines are, let's say, whatever is my website or my service / it has to be noun. Noun means it could be bucket, the bucket name, and then the object name. So here, if you see, these names are nouns, and the verb, the action is in the operation. So you don't need to mention the verb here. But there is, we didn't cover REST API in the base, in the fundamentals in previous sessions, because it's not really a big deal. In fact, there is nothing stopping me from writing. I say that my service, my stupid API, and internally I can do anything. So when you're developing API, there is nothing stopping you writing your own thing your own way without following the RESTful pattern. But the RESTful pattern gives you guidelines. The guidelines are use the word here, as in the get, put, post, etc., and use the nouns here. So it's not a big thing. You can just read one pager or somewhere, and it should be good to go. And then what are the other things we wanted to do? Put. So whenever my service, I'm creating a new bucket name. So this creates a new bucket name, bucket, and put, my pencil is not
Post.
doing,
Yeah.
and then object name, the same. And the same delete, and the same here. Okay. These are the operations, APIs we will provide. There can be many more admin operations, which are some special case operations, but we don't need to worry about all of them in interview. In a real design, we do worry about all of them. In interview, we usually focus on the frequently used user operations. Yes, someone has questions.
No, I was just saying post also, right? Here we can use.
Oh, yeah, so the post versus post put, there is some theory behind it. You can use post and do the same action. To be see the REST APIs, there is nothing stopping you doing different things there. But the guideline says that put versus post. I recently
Yeah,
forgot.
post creates, I think, new object, and the put updates it efficiently. Like, yeah.
Yeah. So if you are creating a new one, only new one, then I think is a post. But the
Yeah.
put can be new one and also an update. So sometimes in real systems when we develop, in fact, I also went through this ambiguity multiple times. It's not very clear at times. Should I use a put or post? So based on that particular scenario, we pick the right one. So um, but actual system is not going to stop you from doing different things. It's just a guidelines. It's good to have a guideline, understand the guidelines, because nowadays all companies are using REST APIs. Some interviewers are asking, my ex-colleagues told me, so better you have a read about that and have an understanding. You don't need to worry about all different possible REST APIs. Get, put, post, delete. I think sometimes patch as well, but you don't need to worry about all the other REST APIs. Now we came with functional, non-functional, and APIs. Let's come to the estimates. So here estimates, we have not designed the system yet. At this time, estimates may not be accurate or correct. We are giving approximate numbers. Why do we give approximate numbers before designing the actual system? Because when we are before developing a feature, we usually need to calculate how much storage we need, how much data centers, appliances storage we need. We need to tell the infra team, okay, we are planning a big feature head. We probably need this much of amount. So you need to have some planning upfront. That's the reason we give estimates. We take some approximate numbers and make estimations, but actual numbers, if you want accurate numbers, we have to come back to estimates again after the actual system design. Okay, we will come back, but we'll give a number. Now coming to estimates. So see, estimates varies differently based on the application. For S3 kind of system, if you see who is using S3, most of the times it's corporates. Their file sizes are usually slightly bigger. Their storage amount they buy is also quite bulky. They buy petabytes of the storage. And then, so for example, each organization, let's say organization 1 buying 10 petabytes, organization 2 buying 2 petabytes, so on. But the number of such users, because there are big users, usually are smaller. Let's say 500 million users. This is for S3 kind of access pattern. Whereas if you go for Google Photos kind of patterns, Who are the users? We are the Google Photos users. So our, what do we do, how much we usually buy in our Android phones? I usually buy only 100 TB. I'm very greedy, in fact. So people usually probably buy 200 TB because only for the photo storage and the Google Drive. But the number of users are billions. There are many Android users all over the world. So this is a different business model. If you understand, in fact, as a founder of a company, you need to understand the business model. This is a low margin, but high number of customers. Margins are lower. But here, if you see the kind of work pattern, margins are higher because they are corporates, they pay higher. But the number of such users are lower. So if in this case, when you're making estimations, if the question says specifically, I will need to develop a photo storage system, or a music storage system, though in those cases, you take estimations in this style where have higher quantity but lesser storage for each of them, each of the customer. Whereas if it is like a platform as service, something like S3, then you do this way, less number of customers and higher storage for each of them. In case interviewer itself gives the numbers, then it's good. You just go with their numbers. But now for the calculations, I'm estimating S3 kind of storage numbers. Let's say each customer is buying 10 petabytes of on average. Let's say it could be someone probably taking higher, someone taking lower, but I'm just taking average number, 10 petabytes. I'm assuming 500 million customers. Okay. In that case, total how much here they are buying, customers are buying storage. But in case if customers are buying number of objects they can return, then we have to take the count and then we need to assume average size for each of the object and then derive the storage from that. But usually we buy the storage, not the number of objects. So in this case, how much throughput can it be there? How much storage can be there? These are the two things we need to calculate: total storage and total throughput, because based on that we need to design or plan our system. How much is this total storage? Can anyone tell me?
It's 5 into 10 raised to the power 9 petabytes.
Yeah, so 10 petabytes into 500 million. So 500 million, if you see here there are beginners as well. If you think that I'm explaining two basics, but I need to explain because there are beginners as well. KB, which is usually 2 power 10, which is at 1024, but we usually assume it as a 10 power 3. It's more easy for the calculations, not you can just round it off to thousands. And the corresponding in the units of the decimals, it is thousands. Okay, then MB 10 power 6. See, it just plus 3, plus 3, plus 3. Go on. 10 power 9, 10 power 12 is simply just plus 3. 3 is the magic number here. Probably you understand the concepts well, but when you're making actual calculations, you get confused. I understand until it becomes a habit, second nature, it is confusing for everyone. Okay, there's nothing wrong in that. In this case, if you remember M, million. See, this is 10 lakhs. 10 lakhs is a million. If someone is from India, 10 lakhs is a million here. Then what comes after million? Billion. And this one is GB, MB, GB. Just remember this order and this order. After GB, what comes? TB. After it comes PB, petabytes. And billion after billion, trillion. No, did I calculate? Yeah, T, see, T and T here matches, M and M here matches. Remaining this doesn't match, but so you will get used to that, learn them. I think 10 power 15 is quadrillion, I think, but you don't really worry. You can just mention in the trillions all the time. So maximum, okay? If you thousands, millions, billions, trillions, quadrillion, KB, MB, GB, TB, okay? Now, you remember these two entries and derive upper and lower numbers from there. Okay, I'm not saying to mug up, but this is more easy for you in the interview when you're stressed out and your brain is not giving you numbers easily. Then this is more easy way for you to calculate at that time. In normal times, everyone makes calculations right. But in the interview, people are stressed out. Their brain stops working at times. So just go with this kind of hints. Okay, now what happens here is if you see 10 petabytes, 10 into how much is a peta? 10 power 15, sorry. Yeah, yeah. 10 power 15 into 500 million. How much is a million? Million 10 power 6. Okay. If you see, there are 500 million users, each of them buying 10 petabytes. This is the average or whatever worst case you can say. Then if you just round off numbers into calculate total number of zeros. 15 plus 6, 21, 21, 22, 23, 24. Totally 10 power 24. And this is 5 into. So if you see, if you mention this in the storage wise, petabytes 10 power 15, so 10 power 15, oh, it's just going to quite high actually. Actually, with the number, the petabytes, we took quite bigger number. So this total storage also coming quite bigger number. So this one is TB. Then 5,000 into 10 power 6 into 10 power. I'm trying to give you this number in the terabytes, sorry, petabytes, because that's usually the number we usually give. But this is going to be quite high. We can probably just take a smaller number.
Maybe we can also reduce the number of
Yeah.
users, because 500 million is also big number. Yeah.
500 million is for this style not a big number, but 10
Okay.
petabytes is a bigger number. Okay.
Okay.
Yeah. So you can just leave it here as well, but usually you can take a smaller numbers if you want to be comfortable. So what interviewer wants to say, unless they give the numbers, they want to see your ability to do make the calculations. Okay. I will take less the TB, so I can give you easily how to give numbers. Let me take it. In this case, TB is 12, and then when you add up, it becomes 10. Still, it's quite bigger actually. 5, just without this itself is 5 petabytes, and with this 10 power 6, it becomes quite bigger number to explain. Yeah, I think this one also I have taken quite bigger number, but this is S3 range, so obviously it's going to be quite high. Let me take another one. Let me come to the throughput. Now, throughput wise, how many total number of requests can happen at one at a time? At a time, not all the objects may not be having read or write operations going on at the same time, but assume half of them are going on. So how many total requests can have in 10 TB? Let's assume each object and an average of size around 5 GB, let's say. So total number of objects possible, 10 into 10 power t again, 12 into 5 into G. So G is 6. Or G is 6. Did I forget? No. Yeah. The G is 9, sorry. Yeah. Now, if you see cross out 3, so this is 2. So 2K. Sorry, did I do it wrong? Yeah. 2K objects. How can it be 2K objects? GB is bigger size. It has to be. If you take one photo, usually one photo is around 4 MB, and even one music's media is also around 5 MB. So we need to take in MBs. This one is 6, 10 power 6. So it comes back to 10 power 2 into 10 power 6. That means 2 million objects. So 2 million requests it is. Oh no, sorry, I got really confused. So throughput, total number of, total number of objects and average could be 2 million objects. And each, if assume that the operations are going on each of them, read write operations are going on each of them, maximum throughput is 2 million. Did I calculate it correctly? I think somewhere
Yes.
okay. I think I'm confused because we started with petabytes and then I moved into terabytes. Yeah. Okay, let's come back to the estimations. Once we are done with the entire design, let's take a clear number and start with this numbers again. And yeah, so you're giving the throughput, total storage we need, how much throughput we need, because throughput that tells us approximately how many machines you need to deploy and how many replicas you need to have to support corresponding read and write operations, etc. Does anyone, someone has question? Yeah, multi-load upload. Yes, multi-load upload is also a feature that comes as a functional requirement. And you can say that multi-load upload is actually not difficult. Actually, multi-load upload is like a bigger object, but you can also say that I will come back to this if it is. It's a good to have, and I will come back to this if we have time. Okay. Usually, interviewers also say that they want to try to make the design simpler, so they can also say that okay, we'll look into that later. Let's go come with a simple basic design first. Okay, that's multi-load upload. Okay. Yeah, any questions here before we jump into the high level design? Does anyone have any questions?
No, we can move ahead here.
Okay. Now we come to the high level design. In the high level design, so how the aura system looks like. We that don't directly jump into the deep dive because they just want to see your ability to picture the entire design in high level. So here there are end users here, and all of them sending the requests. Let's say if you assume S3, something like S3 load balancer, kind of, it's a load balancer here. And then from the load balancer, the requests go into different internal services here. The internal service, let's assume we are going to have multiple services, and each service is having multiple instances running. So one of them could be data uploader. So you gave data, object uploader, a data uploader, and there can be multiple such instances because we try to have these services stateless, and we keep the actual state into the data storage system. Data uploader and then data reader, multiple such instances of the data reader. Actually, metadata manager doesn't need to be exposed out. There can be another service, metadata provider, metadata manager. And the data uploader and both data leader both can be communicating with the metadata manager. And then data upload, something like bucketing. What other services do you imagine? In the high level design, what other services do you want to have? We can we look into the security services like encryptor, decryptor, so on. So but that we wanted to have it as a good to have later on, so we can extend the design in the next upcoming session for the security. For now we are looking into the basic system. Okay. Yeah, bucket manager, you can say when we want to create new, when a request comes for the new bucket, we can create them, bucket managers. And user permissions access, whenever someone is trying to read or write a object, we need to check the user permissions. Or you can say permissions checker, or you can say access controller. Okay, so on. But all of them do internally communicate with the metadata manager. And all these services, we always remember these intermediate services need to be stateless, because if the number of requests are going up, if the throughput is going up, we can just have one more instance of it deployed and running without really have to worrying about restructuring the underlying storage. For example, I'm getting too many write requests, I can have another data uploader instance running. But actual storage, the actual state has to be in the data layer. So this is all a data layer. Just because of the picture doesn't mean entire data layer is going to be on a single machine. It could be, this could be different data centers as well. It could be one data center, these two could be another data center, and there could be replicas among them, so on. But in high level, we just picture one data storage layer. This is the storage layer, we can call it. And the metadata services, data uploader, data leader, all of them read from the actual data storage layer. So here what we're doing, we're trying to make the services here stateless so that we can deploy them more and more and decrease them if we don't want. But the storage layer takes care of rebalancing, restructuring, replication. So whenever we need to expand the storage layer, we just have to worry only at this layer. Actual services layer doesn't have to worry. Similarly, during the shrink, etc. So all the clusters, operations, everything comes here. And the data services layer are clean without state here. Okay. There can be some situations where we need some states in the intermediate, but usually we try to have the intermediate services stateless. And whenever you need to have a cache service, you usually introduce the cache service between this, the services and actual storage layer. Here you can introduce the cache service. Okay. Now, this is the high level design. Now, once we have the high level design, my picture is really bad actually, sorry. We then get into the deep dive. And for the deep dive, what do we do? At every level, how are you going to handle as the more and more requests are coming? How are you going to handle the throughput? How are you going to handle availability, scalability, so on? So from different angles, you think from each level and expand the system and deep dive into the system and explain to them how it's going to work when this happens, so on. So are there any questions till here?
Can you explain the cache briefly? Like
Yeah.
what is the cache service?
So we actually here in the high level design, we don't need to really write the cache here because right now we didn't justify why we need a cache, but usually we need a cache, but we didn't justify. Once we deep dive into the storage layer, then we explain why the performance and the latency may not be sufficient without a cache and why we want to introduce a cache and where we want to introduce the cache. That's when we go into the deep dive. That comes in the next stage. At this stage, in fact, you don't need to even drive the cache layer here. I just wanted to mention that cache layer sits in between these two. In high level design, you don't need to drive here. Here, just because we want to have cache, we don't want to say that we want to have cache. We want to say what do we want to cache, where exactly it has to sit. And cache can be in multiple stages. It can be somewhere here for different purpose. It can be somewhere here for different purpose. So once we dive into the storage layer, where exactly we have to read from the disk again and again, and how do we avoid that by introducing the cache, and what kind of format the cache is going to have, that we will explain in the deep dive.
Okay. There is one more question in the chat.
Can you please ask whether we need to set it up in SC or will it be automatically loaded for beginners? Where do we set it for up means multi-upload? Are you asking about the multi-part upload?
So yes, I'm asking for the data uploader and also the balancer.
So, but the multi-part upload is a feature that S3 particularly provides. So when the file is quite big, let's say I'm trying to upload 1 GB of the file to the S3, and because it goes data entire bigger file goes into goes to the actually someone mentioned it's more than 5 GB. Let's say I'm uploading 500 GB file. It's quite bigger. I'm trying to upload to S3, which is the data center might be sitting in US or somewhere. And because the network is very inconsistent, whenever the network connection is broken, that entire upload fails. So instead of that, what you usually do as a user, when you are uploading a bigger file, you know that it's a bigger file. I think in the API itself, there is a flag. You mentioned that this is a multi-part upload. When you mention that the S3 client operation, it will divide the file into chunks and upload each chunk. And for each of the chunk, whenever it is uploaded, it checks that, okay, am I done till here? Am I done till here? It tracks. So by any chance, if network connection breaks, you don't need to start all over again from the zero. So here, if you have a very big file, when you are uploading S3, let's say put or post, whatever it is, my S3 bucket name and the object name, and then you give the file. Okay. When this file is quite bigger, if it is bigger than 5 GB or whatever size it is, I don't know the limits, it divides them into chunks internally. You don't need to do anything. It uploads each and everything into the S3. Okay, it uploads here, this one uploads this one, uploads this one, and it at every stage it checks, okay, how many chunks did I get, till where did I get. Okay. And in case if for the performance reasons, if it is uploading parallelly, for example, it has two uploaders running, and it has uploaded these three, and it has uploaded these three, then still S3 can maintain the status that I got these chunks, chunk 1, 2, 3, and 6, 7, 8, so on, but I didn't get these chunks. So S3 can maintain the status. Now, if the network connection is broken, the client can just send only remaining chunks. It doesn't have to start from zero all over again. I think that's the reason why multi-plot upload is there. I'm not very sure. I didn't use this S3 APIs much, in fact. So, but this is my guess. This is my understanding. If anyone is having experience with the multi-part upload, you can mention, you can explain as well. So when the client is uploading, they can mention this is a multi-part upload. Okay, tracks and keeps them in under S3 feature. Yeah, someone mentioned, that's correct. Denise, tracks and keeps them in order S. So when you are uploading multiple, it breaks a bigger file into chunks and uploads them parallelly, and it tracks which chunks are done, which chunks are not done. So you can, when the network connection re-establish, you can upload only missing chunks, not entire file again. Yeah. Are there any more questions before we go into the deep dive? Okay. If you don't have any questions, I can continue. My eyes seems fine now. I can continue for another half an hour. Rajni, do you want to drop out? You said you need to drop out. Looks like she left. Yeah, looks like she left then. So is everyone ready? Okay to continue for another half an hour, or do you want me to continue the deep dive in next session? Because anyhow, we can't complete entire design in another half an hour.
I think it's fine. We can continue for half an hour, but like you can decide if you're feeling like to continue.
Yeah, I'm fine. Yeah. So now we got a high level design. Let's get into the deep dive. So what do we do? What we do in the deep design, in the deep dive, for every stage, how are you going to have the scalability and etc. So and so, etc. For these levels, we already discussed how we is going to scale the load balancer. We discussed this in the fundamental sessions about the load balancer. And these are stateless services, so it's more easy to scale, as in more if we need to do more work, we deploy more instances. And this is possible only because these are stateless. And if we don't have too much work, we can reduce the instances as well. So this is also fine for the scalability. And now what we need to worry, especially in this design, because this is a storage as a platform, we need to focus more at the storage layer compared to other layers here. Now what happens, let's say you are given a big machine, appliances, data centers, and asked you to build an object storage on top of that. So in each of there are many more disks, and this could be one data center. This could be another data center with more set of disks. So it's your responsibility to format this disk into such a manner to store the objects efficiently, and you need to track those objects metadata as well. So what do? We format, we take a disk. Whenever there is a object write operation, we write the object, let's say O1, O2, so on, 3, so on. Then the metadata need to be maintained. So the operation, if you see the write operation, put whatever the service name and the bucket name and then the object name. So the mapping has to be like so, given a bucket name and an object name, what is the object ID? Okay, so we need to use our own ID. We don't do the actual mapping just based on the names, because these names can be renamed. Object my this could be my object can be renamed to your object. Object 1 can be renamed to object 2. So we always need to have one abstraction layer which is mapping the names to the IDs. That way we are allowing and rename operations. Okay. Now one mapping object name, bucket name and object name to the object ID. The other mapping is object ID to the object locations, actual disk block locations. So for example, one object, object 1, okay, this object 1 can be, let's say, 1 GB size. In 1 GB means even if you write contiguously and even if you write full data blocks, how many data blocks is going to take? 1 GB by 4 KB. Usually actual data block is slightly less than 4 KB because we do write headers, footers, so on, so checksum, etc. So slightly the actual data going to be slightly less than 4 KB. But even if you assume so, how many data blocks it takes? 10 power 9 by 10 power 3. So it's like 10 power 6. Okay, these many data blocks the actual write operations takes, and these objects need not be contiguous in the same disk. It could be somewhere here because when we are writing the data, the object storage tries to write them in sequentially in adjacent places, but there may not be place all the time. For example, this while this was getting written, object 1 was getting written, probably these data blocks were allocated for object 2, which is parallelly getting written by another customer. So there may not be place immediately. Or when the object X was written here, it got deleted. That means the 3 data blocks are free here, but 2 more data blocks are free on another disk. Okay, so all the data blocks need not be contiguous for the object. That's the reason we need to maintain an array of locations. And this could be indeed different data centers, different appliances as well. We never know. So we always need to maintain the abstraction. So we need to say that this object 1 is written data center D1, DC1, and then disk, let's say disk D1 at the offset 1024, for example. Another block written DC1, D1, let's say 401 data block, right? So it could be somewhere around 8196, for example, so on. Okay. And then the data block could be DC2 and so on. So object ID to the actual locations, including the data center, disk, and offset exactly where it is written. This mapping has to be there. This is the metadata layer. So what happens when a write request comes? We first look into the first operation in the metadata. We check the free disk mapper. There should be free space map manager, the service name, the free space map, which maintains, okay, on the each and the DC1, what are all the free places? What are the D1 and the disk 1, what are the free places? DC2, what are the free data blocks, so on. So look into the free spaces and go pick them. For example, if the incoming request is 5 data blocks, try to pick which are contiguous by 5 data blocks. What we usually do in real storage systems, we do maintain a bitmap 1010, so on. We look for contiguous 5 ones. These are bit level operations, but this really low into the systems. But that's so we more easily find out contiguous 5 free data blocks by looking for 5 ones in one contiguous range. But that's very low level. We can come to that if you have time. Then we find a free space and allocate them, then go and update this object ID to the disk locations mapping here. And then when the get operations comes for the same, we go and look into in the get operation, we say that what is the bucket name and object name. Take the bucket name and object name, look up corresponding object ID, then go to this mapping object ID to disk locations. Now, and then look into the disk locations and read them. So these are ordered by offsets, so read them contiguously. Okay. Now we know if we have metadata of the mapping of this kind and data in this way, we can serve, put, and get requests accordingly. But the no question is, no, actual data is stored with our own formatted storage layer on the disk. But how are you maintaining this metadata? Where do we want to write this metadata? There are multiple options. How are you going to write this metadata? One option is database. This is for beginners and people who are not so much into the storage expertise. You can go with this. In this case, you can simply maintain a table of bucket name, order object name, and you can maintain them. You can use a sorted index on the bucket name and order in object name. That way, all the objects belonging to one big bucket are contiguous here, and then their corresponding object IDs are here. So with this option, what happens if you get a request like list all the objects of object bucket 1, you go and look at the first entry with object 1, sorry, bucket first entry with the bucket 1. Now because this is sorted, you can keep reading continuously until all the entries related to bucket 1 read. Look, take these names and list them out. Okay, that's how you're going to support list operation. And the read operation, you go and look up there and take the object ID, another table with object ID to the corresponding disk mapping location, this one. And take the disk locations here and go and read from the actual disk. But this works fine, but this is not efficient. This is for only for beginners, because we are providing the storage as a platform and we have customized our own storage. We have complete control over the storage. We really do need to introduce a database layer, because database layer is costly here. It is not very performant as compared to having our own custom storage, because database every read operation, it has to follow ACID properties. It has to follow transaction properties. So a database has to do a lot more internally. But for in this case, all that we need is a mapping. We don't really need any of the other features of the database. So we don't really need to introduce the database and increase our latency and impact our performance. In fact, for S3 kind of storage systems, they don't use the database here. The other option is you can have the similar instead of database, you can have your own key value store, something like Redis, with the persistence, because metadata has to be persisted. If you are using key value store here, if the system is crashing, you should be able to record the metadata, right? So it need to have the persistence. But the actual for any advanced senior engineers at staff level or principal in level, or people with the storage expertise, you always go for actual custom storage layer for the metadata. So what we can do, because anyhow we are having complete control over the storage, we usually, the way how file systems works, if you understand that, it is very similar here. We do usually have a super block. Super block contains a pointer, the address of the mapping to the bucket name to the corresponding of special objects. You can say the special objects which are maintaining the mappings. So let's say buck1 and the corresponding special object ID O1, and this O1 contains object. There are two mappings. It has to has first. Okay, this object, what are the user permissions. Who are all the users can read and write this object. See, while only one user is creating an object, read and write permissions can be shared with the other members in the team, in the organization. So multiple users probably have permissions to read and write an object. So user permissions, and what is the object ID here, and sorry, object one, bucket one, sorry, I'm sorry, this is not actually. So this special object ID, this special object contains mapping of object name to the object IDs, and then another special object which contains object ID to the object locations mappings. Okay. Now this object looking at these mappings are all stored as a typical typical object storage. So similarly, the way we are writing the objects, data as objects, we can write the metadata as well as an object. So we can use the same logic, creating them as an objects, but those are special objects, maintaining the metadata here. So with this, what happens when there is a put operation? What happens? You go to superblock, you go and look into the object name, bucket name to object name mapping. See if there is a new bucket exists. If the bucket exists, go and take the corresponding special object address. Go there, and then take the object. Look up object name here, and take the object ID here. And corresponding look into this mapping. This will maintain both the mappings. Look up the object ID here, and then from object ID to take the object locations here and go and read the actual blocks for the actual data. So this is all maintained in the data now with our database in our own object storage, in our own customized storage. But here there are two problems. One is the file can be too big, that this single special object of fixed size may not fit in for all objects of a given bucket. So what usually file systems do, they do use something like B-tree structure, where are intermediate nodes, and then so on, intermediate nodes, and then leaf nodes. The leaf nodes contains actual mappings. Intermediate nodes tells further where you need to go further. So for each and every mapping, you can mention, is it a actual, there can be a flag, is it actual object or a indirect block. So if it is an indirect block, you take this object location, go and read that object location, and again look up it could be mapping until you see a 0. If it says 0, it means it is actually having the original mapping, the actual mapping of the object ID to the location. So indirectly, you keep doing so and so, and you create an actual B-tree structure here, indirectly create a B-tree structure here. Okay. And this is all actually in the storage layer for advanced storage users. In the next upcoming session, I can give you a neat diagram. I couldn't create a diagram for you this time because of my problem. I can take you one example and create a neat diagram so you can understand this better. My scribbling is not good actually. But now the other problem is, if you see, to look up one object data, you need to go through so many intermediate blocks, which this can be discrete read operations. So what usually we do in the data storage systems, we maintain an index in the memory. When file system or the storage system coming up, we read the storage system, we maintain a mapping of bucket name, of object name, and then corresponding object ID and the location, so on. So we maintain them in memory index. That way, first we look into the in-memory index. If it exists, we go and read from the actual object locations directly from here. Otherwise, we go through all this way and then we cache the result here. So this is where we use a cache. When we really use a real system, that's where we need to know, this is where we need to cache and what exactly mapping we need to cache here. So this is how, for the advanced engineers, staff and principal level engineers, they may ask you, why are you using the database? Do you really need a database? What are the alternatives? Other alternatives, key values source with persistence, but they may not be still giving you all the control needed at the low level, because the data is huge. There can be many, throughput is high. So that's when you want to go with your own custom storage and maintain the indexes in memory. So all these advanced topics will come for the advanced users. In the next coming session, I will really give a nice example with a diagram, so that would be better for you. Okay. um, but again, if you see, this entire super block and all this mapping is in there in every machine. So this is per machine. Machine one it is same, and another machine 2 will be having similar structure, so and so. And for all the machines together at the high level, we can introduce another cache layer, or the other option is we can make the partitioning scheme such a way that all the buckets with A to D going to machine 1, all the buckets with E to let's say E, F, G, H going to machine 2, so and so. That way we don't need to really worry about the another layer on top of the each and every machine, and each machine is responsible for only set up the data, and it is independently working. So when a request is coming from for bucket 1, or let's say bucket A, and then object 1, so it goes to this machine. The request coming for bucket E, then it goes to another machine, so on. Okay, and each machine is working independently. But all this is not very clear from this picture, I understand. I will make a nice diagram for you in the next upcoming session. But remember that if you're not good in explaining this, or if you're not understanding this well in after next session as well, you can stick to database or the key value store. And if the by any chance interviewer asks you, why are you going with that, can you have your own custom storage, you can say that I'm not a storage expert. I think this is a solution I propose. You can say that. If you don't know that, you don't know that. That's okay. Instead of giving wrong explanation, that's a better option. You can do that. Okay. Here I will stop the session. I understand I was in a bit in hurry in the deep dive, but I will next session will be with the neat diagrams I can show you. And then we discuss about the encryption, and we discuss about the read-write patterns, delete operations, backup, etc. And we can discuss about the multi-part upload, and also the versioning, and so all the miscellaneous things we can discuss in the next session. Are there any questions?
Mm, I think there is one question in the chat by Denise.
Okay, would it be a good idea to have a CloudFront with a load balancer for low latency? CloudFront with a load balancer for low latency. So do you mean the CloudFront means something like Syrian?
I think she left as well, but yeah.
Okay. Okay. Let's see the next time, because here we are developing S3 itself. That's itself in the cloud, and the latency here is mainly at the disk level, not at the load balancer level. So I need to understand her question. So because the disk level, I don't think cloud is going to help unless we are going to cache some of the recent data in the cloud. Yeah.
Shailen, thank you for the nice session. Maybe can you also share about some links which you were mentioning earlier, so we can just take a look and then we are more prepared for the next session.
I actually, yes, I don't have any links for this one, but the one I was proposing is, if you really wanted to understand the internals of how a typical file system works, and similar to the structure, beta structure, etc., there is one book, The Design of the Linux, I think, I forgot that book. There is one chapter. He nicely explains how a inode looks like, and how this B-tree kind of structure works, etc. Or else you can on the internet Google ext file system design. I will Google up if there are any good ones with this easy diagrams and then send it to you. But it will be the next session, because I'll be giving diagrams for this one. It will be very similar, so you should be able to understand.
Yeah, okay. The custom one was like bit tricky, so yeah. But I think
Yeah,
maybe
so
the
that's
next section, yeah.
that's exactly I said. So that one will be if we have some understanding of how these file systems internally develop, then only we'll be able to explain. That's the reason we need to have a one next in the section. We need to really deep dive on that with proper examples. Otherwise, very tricky to understand.
Okay, thank you.
Okay. Okay, chalo then, bye.
Thank you. Bye. Have a nice day. Evening.
Thank you.